Welcome to lecture 6 of this course. In the last class, I introduced the concept of density matrix. In this class, we are going to discuss the density matrix formalism in somewhat details. So let us begin. In the last class, we saw that the quantum state of a two-level atom can be represented by the state vector psi is equal to, say, CZZ plus CEE, right? So Z and E are the basis states of the two-level atom. Z is refers to the ground state, E refers to the excited state, CZ and CE are the complex coefficient, and this is called a state vector representation. Or equivalently, we also learned about another representation, and that is called the density operator representation. And in this case, the density operator is defined as ket psi and bra psi. So this is an operator, and here psi is a pure state. Actually, I will today discuss about mixed state as well. We'll come to that little bit later. And in the basis Z, ket Z and ket E, this density operator can be represented by this matrix rho, where these matrix elements are rho ZZ, rho ZE, rho EZ, and rho EE. And in fact, in terms of the coefficient, rho ZZ is equal to CZ star, and rho ZE is CZ star, rho EZ is CZ star, and this one is CE star. Okay, and also we learned about the physical meaning of these density matrix elements. Now in general, irrespective of the nature of the atom, if it is an isolated atom, it may have many energy levels. So the state of a pure atom, basically an atom which is not interacting with any environment, an isolated atom, so it can be represented as superposition of the state of the atom, can be represented as superposition of its eigenstates, right? And this is the state vector representation, and the corresponding density matrix representation or density operator representation would be this. For example, for say three-level atom, the state vector psi would be, it will go from I is equal to 1 to 3 Ci phi I, where phi i's are the eigenstate. That means I can write it as C1 phi 1, C2 phi 2, and C3 phi 3, where phi 1, phi 2, phi 3 are eigenstates, and the corresponding density operator would be this, and density matrix element would be represented, the density operator would be represented by, or the density matrix would be represented by 3 by 3 matrix with elements like this: row 1 1, row 1 2, row 1 3, row 2 1, row 2 2, row 2 3, row 3 1, row 3 2, row 3 3. So this formalism can be extended to any number of energy levels. Now, one great advantage of density operator is that we can find out the expectation value of any operator using this density matrix or density operator. So suppose we have a operator A corresponding to a atomic system, and then the expectation value of this operator would be given by just by taking the trace of the product of the density matrix rho and the matrix representation of the operator A. Then this is going to give us the expectation value of the observable A or operator A. Okay, So here actually many times I will not going to write the this head. So you just understand that we are discussing quantum mechanics, so these are operators. Now let me actually prove this relation. It's very easy to prove. The expectation value of operator A is in the state vector formalism, it would be simply given by this, where psi is equal to it would be, I can write it as superposition of these eigenstates. Okay, now what I do, I can just write it. There are two, one is here bra psi and ket psi. So let me use this but with different indices for bra part and the ket part. Then I can write it by two summations, I and j here, and here let me write ci star, and the other one would be okay c. So therefore here I would have phi I a, and this here would have, I have phi j, and then cj is coming out. I think it is easy to follow. Now let me just, this coefficient also I can express in terms of these eigenstates, because we have, say, psi is equal to, say, ci phi I. So if I want to know ci, to know that, let me multiply this by both sides by this bra phi m here, and then the other side also I have to do multiply it by phi m, and you know that these are eigenstates, so therefore these are ci, so they are orthogonal. Orthonormality conditions I have to apply, so this will be ci delta mi. So out of these summations, because of this Kronecker delta, we will just get cm. So this coefficient cm is simply given by phi m psi. So therefore in this expression here, ci cj, ci would be simply phi I psi, and cj would be phi j psi. Alright, so therefore if I put this, so this implies that ci star is psi phi I. So using this I can, let me just take it, I can just put these coefficients. Okay, so what I can do, I can just write it as I j here, ci star is psi phi I, and cj is phi j psi. These are, remember, these are just numbers, these are just numbers, and I have phi I a phi j. So because these are numbers, I can write them interchangeably. So therefore if I just write it as phi j, if I take it this side, this one, phi j psi and psi phi I. Okay, then all right, so what I will have is phi I a phi j. We can see that this is nothing but the density operator rho. So therefore we can write ij phi j rho phi I a phi j. Okay, now again if you see that this is actually, I can invoke the so-called completeness condition, because phi I are the basis states or the eigenstates. So therefore this is identity operator or identity matrix. So using this identity matrix, this completeness condition, if I invoke, then I can write the expectation value of the operator A as, now I have j phi j rho a phi is A. And quite clearly, as you can see, this is nothing but the these are some of the diagonal matrix elements of the operator, product of the operators rho and A, and therefore I can now write it as trace of the matrix rho and A. So hence we prove that the expectation value of any operator can be written or can be found just by finding the trace of the matrix product rho and A. So this is a very useful way to find out the expectation value of any operator. Now let me list out some properties of density operator or density matrix rho. Rho is an operator in the Hilbert space and rho is a Hermitian. So that means rho is equal to rho dagger. That means if I take the complex conjugate of the density matrix and then take the transpose, I'm going to get back the density matrix again, rho. And because rho is Hermitian, eigenvalues of rho are real, and in addition to that there has to be non-negative, and this comes due to the fact that the diagonal elements in the density matrix or density operator represents probabilities, and probabilities cannot be negative. And rho is normalized. This implies that if I take the trace of rho, then we'll get 1, and that is obvious because the diagonal element represents probability and total probability has to be equal to 1. One useful property to remember is that the probability to find the system in a measurement in the state say phi is given by just by calculating this quantity. This is a very useful result in a way and property, and it is worth remembering, and we will utilize it later on. And finally, the evolution, the equation that density operator satisfies the so-called Liouville equation, and that is given by I S cross del rho del t is equal to h rho. This is called Liouville equation. And if you see these equations carefully, that this density, this is not Heisenberg equation by the way, and rho in fact does not satisfy or obey the Heisenberg equation. Recall that if there is a physically observable quantity is there and it is represented by the operator say A in quantum mechanics, then this operator satisfy this Heisenberg equation of motion if it is not explicitly dependent on time. Okay, but this rho does not represent any physically observable quantity. That's why it does not satisfy the Heisenberg equation. So rho does not represent any physically observable quantity. All right, to get an idea about the properties of rho quickly, so let us just consider this simple example. Say a two-level atom is represented by this coherent superposition of state 0 and 1, and in terms of matrices, 0 is, this kth is represented by the column vector 1 0, and 1 is represented by the column vector 0 1, and then this state vector of the two level atom can be represented by this column vector 1 minus I. So the corresponding density operator for this two level atom would be this kth psi bra psi, and if you work it out, then it would be 1 by root 2 1 minus I, 1 by root 2 1 plus I, and then rho would be represented by this matrix. So this is the density matrix for the two level system that we are considering here. Now immediately you can see some of the properties are quite evident, that rho is obviously equal to rho Dagger, this is rho is Hermitian, and then trace of rho is equal to 1, right? And also, if I now, the useful property that I mentioned earlier, say the probability of finding the two level atom in the state, just for illustration purpose, say in the state 0, is, we know actually already the answer from the state vector. The probability of finding the system in the state 0 is 1 by root mod square, so that is obviously half. But what about our formula? What it says, that users have to calculate 0 rho 0, and which is, I can now write it 0 as this bra as 1 0, this rho matrix, rho is half 1 I minus I 1, and this 0 is kth is 1 0. So therefore if you actually work it out, you are going to get a half. So far we have confined our discussion to isolated or closed system, and these systems are completely described by the so-called pure state, but in reality systems always interact with surrounding and it results in mixed states. So let us now discuss density matrix formalism for mixed state. Let us consider an ensemble of two level atoms represented by state vector psi A and psi B. This is an ensemble of two level atoms we are considering, say atom A and atom B, or you can call them as subsystem A and subsystem B for the composite system A plus B also. Then here A is represented by the state vector psi A, which is a superposition of the kth basis state 0 and 1, kth 0 and kth 1, and psi B is also, we can write it as a superposition of kth 0 and kth 1 with coefficients, associated coefficients as gamma and delta here. Now from this ensemble, the probability that one can pick up psi A is say P, and the probability that the state psi B is picked up is 1 minus P. These are statistical probability or classical probability. Now the question is that what is the what one will get if a measurement is made in the basis states, say kth0 and kth1. So actually in this measurement two processes are happening. First of all, one have to pick up either psi A or psi B from the ensemble, and next make quantum measurement, on the picked up state. All right, now say psi A is picked up. Psi A is picked up from the ensemble with classical probability P. After it is picked up, we make a measurement on the state psi A. Then either because of the quantum measurement, the state psi A will either get collapsed to kth0 or kth1 with probability is mod alpha square or mod beta square. So we will get either k0 or k1. And similarly, in the other case, if psi b is picked up, and it will be picked up with classical probability say 1 minus p, then after we picked it up, if we make a measurement, either it will get collapsed to again k0 or k1 with corresponding probability mod gamma square and mod delta square. Now you see, what would be the total probability that the composite system will be found in the kth state 0. Two things are happening. If we pick up say psi a, then the probability that it would be there in k0 would be p mod alpha square, and if we pick up psi b, then the probability would be 1 minus p mod gamma square. On the other hand, the probability that we are going to get the kth state 1 would be p mod beta square, and the other one 1 minus p delta square. So these are the total probabilities. Either we are going to get the whole composite system either in the kth state 0 or in the kth state 1. So as you can now see that unlike in the case of pure quantum system, pure state cases, where the whole system is represented by the state vector psi, that means if you have a box like this, then every time you are going to pick up psi, this state psi with 100% probability. Okay, so that's why it is called pure state. But now that is not the case here in the case of mixed state. So how to represent a mixed state? A mixed state is rather represented by density operator rho, and this is where the biggest advantage of density operator formalism, and this is for the mixed state case. It is defined as rho is equal to we have the corresponding classical probabilities and the state say psi I here. For example, in the above case where we have considered, the density operator for this collection of two level atoms would be simply p psi a and plus 1 minus p psi b. I'm sure you have got the idea here. And if we have say n number of components in the ensemble, so I is going to run from I is equal to 1 to n. Okay, now what about the expectation value in the mixed state? Expectation value of an operator, say O cap in the mixed state. So that would be let us work it out. That would be given by this. So the classical probability and the corresponding state, you just have to sum it up. So this is what you will have. Okay, let us see whether we can get a compact form of this. So to do that, let me invoke the completeness condition of basis state. Suppose I have the basis state phi k, then I know that this completeness condition is satisfied. I can take advantage of this. This is equal to identity. So therefore, what I am going to do, I am just going to sandwich this here. This is running psi I, and let me just do here k phi k. These are basis state eigenstates. Okay, so this is what I have put here, and then I have psi I. Now I can write it as follows, because these are, if you can see, these are just numbers. This is scalar product, so I can take it like this. I can write I summation k pi. I can write it as phi k psi I. This one I am taking it here, and then I have psi I O cap phi k. All right, now I can write it again as follows: k cap phi k. Let me write it as summation sign. Let me take inside here pi. I have here psi I. Okay, so you have O cap and then phi k. I'm just rearranging the terms there, but you see that this guy is nothing but the density operator that as we have defined here. Okay, here. So therefore I can therefore write the whole thing as sum over k phi k rho O phi k. Now you can easily see that this is nothing but the summation of all the diagonal elements of this product of this matrices rho and O, density operator and the operator observable. So this is, I can write it as simply trace of rho cap O cap. So this is the formula we have got even in the case of pure state, and here also in the case of mixed state this is still valid. All right, now the question is how to distinguish a pure state from mixed state. If we suppose we are given a density matrix or density operator, then how can we distinguish a pure state and a mixed state? This is very easy, because first of all both actually pure state and whether it is pure state or mixed state, the trace of rho, whether it is pure or mixed doesn't matter, trace of rho is going to be equal to 1. Properties of the density operator or density matrix that I discussed previously is still valid, and that means these density matrices are normalized. Now to distinguish it, what you have to do, if you just take trace of rho square, in the case of pure state it would be equal to 1 for pure state, but trace of rho square for the mixed state, if you take the density operator for the mixed state and take the multiply it twice and then take the trace, then you are not going to get 1, it would be less than 1 for the case of mixed state. Okay, let me illustrate it by just giving an example. Let us say we have a two-level atomic system or ensemble represented by the system. It is a, if I can write it as a equal coherent superposition of kth state 0 and 1. Obviously this refers to a pure state. I can define this state by a state vector like this, and then the corresponding density operator would be this kth psi and bra psi, and if you work it out, you will get it the density matrix of the pure state would be simply half here, half and half here. Now immediately you see the trace of rho is obviously 1. What about rho square pure? This would be simply the matrix multiplication of rho pure with itself. So you have to take the matrix multiplication of rho pure with itself. So this would be this one, and if you do the multiplication, you will see that you will get here 1 by 4 plus 1 by 4, 1 by 4 plus 1 by 4, 1 by 4 plus 1 by 4, 1 by 4 plus 1 by 4. So therefore we will just have 1 half, 1 half, 1 half and 1 half. So that means it is simply rho pure, and quite clearly we'll have trace of rho square pure is equal to 1. Now what about the mixed state? So let us say we have again a two-level atom, but the ensemble, let me write here, consider an ensemble of two-level atom with equal mixtures of K0 and K1. Okay, so that means there is a 50% probability or half, okay, probability of half to get it in the state 0, or which is represented by 1 0, and there is a 50% classical probability of getting it in the state 1, which is represented as 0 1. So what about the density operator representing this mixed state? That would be, as per our definition of density operator for mixed state, so the classical probabilities are half in both cases. So we have half 0 0 plus half, it would be 1 1 here. Okay, so this I can represent in a matrix form, and if you represent it in a matrix form, so in this case we have this mixed state, so it would be half 0 0 half. Now you see again trace of this row for the mixed state, then it would be obviously equal to 1. But what about row square? If you take the product of these matrices, matrix multiplication, if you do, what you are going to get is, you are going to get here, it would be 1 by 4, it would be 0, it would be 0 1 by 4, and quite clearly trace of row square for this mixed state case, you are simply going to get half, which is less than 1. So this validates what I said earlier, that for the case of mixed state, okay, for the case of mixed state, you just have to take the row square. That means, let me just conclude here just by saying this, that to distinguish it, you just have to find out trace of row square. If you are given a density operator, just find out, take the product of the density operators and then take the trace. Then if you get 1, then that is a pure state, and if it is less than 1, that corresponds to a mixed state. Okay, let me now discuss an important concept called reduced density matrix. Reduced density matrix or reduced density operator. Say we have a composite system A plus B. Many times what happens is that we may be interested in knowing only about the system A or only about the system B. Okay, for example, later on in this course we will have a situation where, say, we have a mechanical oscillator like this, and this is interacting with lot of photons, or the mechanical oscillator is, say, butted on a photon or surrounded by lot of electromagnetic radiations. So, or equivalently speaking, I can just depict the whole thing like this. Say I have this system A is there, and it is surrounded by a lot of photons. So this we may say to be as our surrounding, and this as our system. So now if we are interested only in the system only, the question is how to extract information about the system A from this composite system A plus B. Or I mean to say that suppose I know the density operator for the composite system, which is, say, row A plus B, then how I can get information, or how I can write the density operator from row A plus B. Or similarly, if I just wanted to know about system B, or I want to write the density operator for system B, how I can do it if I know the density operator for the composite system. So this is what is answered by the prescription called reduced density operator. So how it is done? So properties, let me write here, properties of system B or A, say system B may be obtained by taking partial trace over the system A. I will explain it with some example of say system A. So partial trace essentially averages out the effect of unwanted system and extract the properties of the system of interest. Okay, so suppose I want to know about system B, then I just have to take trace over A. Okay, I just have to trace over A on the density operator rho AB, and this is basically known as tracing out A. Or if I want to know similarly for system A, then I just have to take trace over B, trace out B. To give an example, let me explain it with an example. Let us say I have this composite system AB, and it is represented by this density operator rho AB, who is, let me write it, say system A is represented by say this ket alpha bra alpha 2 here, and then this is say system A. This is system A, and system B is represented like this. This is my system B. Okay, now when I say if I want to know about system A, then I will just take trace over B, trace out B from a row AB. So I will just take trace, so alpha 2 here cross beta 1 beta 2. Taking trace over B means that I will just take the basis sets in the Hilbert space of the system B, and then I will take the trace. So because I am just taking the trace over B only in this system, composite system A plus B, so therefore this one that is belonging to system A would remain unaffected, and I just have to take trace here on this beta 1 beta 2. So hope this issue is clear now. When I say taking trace over me means I just have to deal with this guy here. Say we have a basis states. We have basis states, say phi I. We have a set like this in the Hilbert space of the system B. Then trace over this system B, I can just write it like this. I will take it as phi I beta 1 beta 2 phi I. Okay, and this all, of course, I can write it just, I can, these are numbers, so I will write beta 2 phi I beta 1. Then I can use the completeness condition. As you know, the completeness condition is now, by now it is very well known to you, so I will simply get it as beta 2 beta 1, and therefore I get my system density operator as beta 2 beta 1. This is just a number, and then I'll left out with this operator. Okay, that's how we can work out. Similarly, system B, if you work it out, you will get it as alpha 2 alpha 1, and this would be beta 1 beta 2. I hope it is clear. So let me give an example. Let us say consider two two-level atoms, two two-level atoms A and B, and say they are entangled, and this entangled state for the composite system AB, they are represented by this state, this entangled state is say in Kate 0 and Kate 1 basis. So you have this is what I have. This is the entangled state. That means if the system A is in the Kate state 0, system B is also, or the atom B is also in the Kate state 0, and or if the atom A is in Kate state 1, then it is the system B is also automatically in Kate state 1. Okay, this is what it means. In shorthand notation, I can write it as 1 by root 2 0 0 plus 1 1. So just understand that the first element in this Kate vector here represents it belongs to atom A, and this belongs to atom A, this belongs to atom B, and similarly here this belongs to atom A and this belongs to atom B. So these things just you have to remember. Then the density operator for this entangled system would be, we can work it out very simply, and that would be half. If I expand, I will get 0 0 0 0 plus 0 0 1 1 plus 1 1 0 0 plus 1 1 1 1. So just remember that again. Let me emphasize that this is belonging to atom A, this one belongs to atom B, this belongs to atom A, this belongs to atom B, and so on. Okay, now suppose if we are interested in the two-level atom A only, then if I want to extract the density operator for atom A, then I just have to trace out atom B, and that is now easy to do. So let me show you how you will do that. You just have to take density operator rho AB is already I have written here. Here I have written it. So let me just write half, and I will take trace over atom B. So half here, this A would remain unaffected. So A from here I take, A from here I take. Okay, this is what I take. A I have taken, and then I will take trace on B, B part here. Okay, this I think you can easily see that this is your B, and this is again from B. And similarly I can just go on writing the other terms. 0 1 I have trace 0 1. You have to be careful, and then you will have third term will give you 1 0. This belongs to system A, so I will take trace over this B, 1 0, and then finally I have 1 1, and then I'll take trace, I have 1 1. All right, now already I got this result that when we have taken trace, here you see when I have taken trace like this, so this would be simply this scalar product like this. So this one is going to give me if I take trace, this is going to give me 0 0, and I know that this is, they are normalized, so this would give me 1. Here it will give me 1 0, and because this Kate and this Kate is orthogonal to each other, so this is going to give me 0, and here also I will get it as 0 1, and this is going to give me 0, right? And finally here I will get it as 1 1, and this is going to give me 1. So therefore we will left out with this one, that would be rho A would be equal to half 0 0 plus 1 1. So these are the terms that will be left out, and this is the density operator or density matrix for the system A. Let me stop for today. In this class we have learned about the density matrix formalism. In the next class we are going to discuss about quantum harmonic oscillators, which is actually one of the most important and critical component of quantum technology. In particular, later we'll learn that how electromagnetic fields could be modeled as a infinite collection of independent harmonic oscillators in the quantum regime. Thank you.